Okay, lecture 2, isomerism. This tends to get students is these isomers. What we're trying to do is create a molecule that has different bonding than another molecule, but it has the same formula, same number of carbons, same number of hydrogens. And later on we'll see we add in oxygens and other atoms, but right now we're just dealing with hydrocarbons. Here's some, you should know the definitions of these terms. Now, draw 5 constitutional isomers with the same chemical formula as heptane. Now I'm going to draw out the condensed form. And the thing is, these are not what, let's see, 1, 2, 3, 4, 5, 6 lectures that have absolutely every bit of information. What these lectures are about is that you is using the information from the textbook, and I talk about most of the information as I go along in the problem, but your textbook is a fantastic resource to get the theory and get the idea of what we're going to be doing, and then I go through problem after problem. I do lots and lots and lots of problems in these lectures. But I do definitely cover the theory as I move along, but I'm not going to break it up and go through all of the theory of the isomers. And you want to read that, and now this is the application, the kind of thing that you'll see on the exam. So use that book. Now, the bonding scheme here, we can see that we have the carbons on the ends are only bonded to 1 carbon. Each of the carbons in the center here, each of them is bonded to 2 carbons, all the way down the line. Now, so what we want to do is create a different structure. And how I do this is, we have 7 carbons in a row. I do 6, and I've left that 1 hydrogen off for a reason you'll see in a second. And as you learn how to do this, you'll know that you have to do that. If you don't, you'll come back and have to make that change. So if I put a 2 there, you'd see that we have to change it. But I take one of the carbons off the end and shift it over to another carbon, creating a branch. This has no branches, it's a straight chain. This has a methyl group that branches off from the straight chain of 6 carbons. Notice this carbon, all the carbons have 4 bonds to it. The bond is either shown or you can tell that it exists because of the hydrogen. Now, if you count the number of carbons, you'll see that there's 7, and the number of hydrogens is 16, just like this guy. But this carbon here is bonded to 3 other carbons. We don't have to look any further than that because there's no carbon in this one that has that bonding scheme. So this is definitely an isomer. It has same formula, different chemical structure, different bonding scheme. So once I've done that, and I have that chain, what I do is I move the methyl group down the line and see if I create a different one each time. And I'm just going to be careful here. There's 7 carbons. I wish I hadn't chosen heptane, but you want the smaller chains don't have as many isomers to work with. We want 5 here. Now, notice that we can think of this carbon as being bonded to a methyl group, or a 1 carbon chain, a 1 carbon chain, and then a 4 carbon chain. This carbon, that's where I move the methyl group, it's a 1 carbon, 2 carbon, and 3 carbon chain. So even though this carbon is bonded to 3 carbons, like this one is, each of these carbons then goes on to do something different than up here. It's a 1 carbon, 4 carbons, 1 carbon, 2 carbon, 3 carbons, different structure, so it is an isomer. So these are both isomers so far. Now let's do this one. Let's move the methyl group down the line. And the reason I do it this way is because then you don't miss anything as you go. If you follow this rule and we're just sticking with alkanes, you'll catch everybody. Now look at this guy. This carbon has a methyl group here, and it looks like it's something different, but notice that it's a carbon bonded to 1 carbon, to 2 carbons, and a 3 carbon chain, just like this guy. All this molecule is if we took this molecule and flipped it, it would look just like this one. Except, when you flip it, the carbons are backwards, but remember, the carbons only represent atoms. Atoms are perfectly spherical. So if you took this and flipped it, you'd have the same exact structure. So you should also get used to that molecules that look completely different from each other, or look different from each other, are actually the same thing. So think of the bonding here. This carbon has a 1 carbon chain, 2 carbon chain, and 3 carbon chain attached to it. This has a 1, 2, and a 3 carbon chain attached to it. So we can't use this one. it's the same one. This is what gets most of the students. They create the same molecule over and over, and then I have to just mark. I look at it and say, no, that's wrong. That's a copy. That's a copy. I've had students who have made up different molecules or seemingly different molecules. I ask for 5 of them, and they write the same 5, but they'll one of the things they'll do is they'll change the conformation, which is something we're going to talk about. So they take this, very common. I'm not making fun of the students, trying to point out what they do. They'll look at this, they'll say, well, let's put the methyl group on the end, move a methyl group over here, but notice this is the same chain. It's just kinked. This is not a kink in the chain. This is an actual new branching because it's changed the bonding scheme. But this is just 1, 2, 3, 4, 5, 6 carbons with the methyl group on 1, 2, 3. Same thing. It's the same. These are equal. These are equal. So we can't use that one. So you got to be careful. That's what really gets the students. So now, since if I move the methyl group over to here, it's going to be the same as this one above, this one here. And if I move the methyl group over to this one, it's just extending the chain. We now go to 5 carbons. Now, when we go to a 5-carbon chain, that means that we need to put 2 more carbons on, so we have 2 branches here. Count them up. We have 1, 2, 3, 4, 5, 6, 7 carbons. 3, 6, 8, 9, 10, 11, 12, 13, 14, 15. Let's see. 1, 2, 3. Oh, this should be a thing. Yeah, I was going to say 15 I only had 15 hydrogens. There's the 16th. On the end, that has to be CH3, so I'm glad I did that. Threw me off a little bit. I do these problems, I make them up, but I don't really solve them normally until I start doing them. So there'll be a few little blips. Any big mistakes, I just redo the video. So anything like that, it's a little embarrassing for me, but it's things that happen to students, and it's good to see. So I went back and double-checked the number of carbons and hydrogens. I was missing one of the hydrogens, and it was because of I had this as CH2 rather than CH3. So all this kind of stuff happens. Always go back and double-check your work. So we have 3 so far. We need 5. So it's looking. So what we do is leave one of the methyl groups alone and move the other one over, and you can see that, or you should be able to see that there is a definite difference here. The methyl groups are next to each other. Now they're separated. They're not part of they're not extending the chain. The chain is 5. They were just moving these along. So now we have our 4th, but you can see if we move this methyl group here, we've extended the chain. That's just a 6-membered chain with a methyl group at carbon 2. We already have that. If we move this one over, then it becomes this molecule, so we can't do that. So we could go to 4 carbons, but what I normally like to do then well, actually, yeah. No, we'll stick with 5, and this carbon can certainly handle 1 more carbon attached to it, so that's what I do. And now this carbon has 4 carbons attached to it. That doesn't occur anywhere else in any of our other molecules, so this is definitely an isomer, a new isomer I should say. And check the bonding, and then you can count them up. 1, 2, 3, 4, 5, 6, 7, 3, 6, 9, 10, 11, 12, 13, 14, 15, 16. This is a new one, 5. On the exam, I tend to make it a little easier. I make sure that there's a lot of isomers to choose from. We were really running out here, but that's nice. Here's some more practice. Draw all of the constitutional isomers with the same formula as butane and for pentane. This is easy to do. That's why I gave 2 of them. Here's our, I don't know why I'm drawing the expanded form. I really hate to do that unless I have to. Sometimes you have to do it for the for reactions, but otherwise it should be the condensed form like this. Now, so if we have 4 carbons for butane, again, you got to know these names. You have to know them right off the top of your head. I'm going to be using them in these lectures as if you know them, and you should know them. We can't put the methyl group on the end because that just extends the chain, and we'd be back to this molecule. We have this, and so we have 3 carbons, and then 1 methyl group we put on the center. Well, that methyl group cannot go anywhere else without just extending the chain. And if you, I'm not going to go any further with it. This is the only isomer of the butane. So butane, you have your butane, or N-butane they call it, and this is the one isomer of it that's a hydrocarbon, unsaturated hydrocarbon. And try it. See if you can. What I would do is, if you don't believe me, and there's no reason that you have to believe me, because you can prove it to yourself. I'm not going to go any further because I know there's nothing else to be done here. Try it though. Mix and match, but look back. No matter how ziggy, you say, well, maybe we do this. There we go. That's new. There's 2 methyl groups, but look at what you get. It looks like there's 2 carbons and you got a methyl group on each, but no, it's a zigzagged, kinked butane. It's just all you've done is move this methyl group, which they're free to do. These molecules are very bendy. You just bent the molecule into kind of a horseshoe shape. You haven't created a new molecule. You haven't created any new bonding scheme. Now let's look at pentane. Because it has 1 more carbon, it should have more isomers. I don't know how many more. I think there's actually a list in your book somewhere. On page 327 in this book, and it says that there are 3 different forms. Well, that's the first one, so let's go try the second one, or try to find a second one. There we go. That's another one. And then if you move the methyl group over, you see that's just a reflection of this one, so that's when I go to 3 carbons, and the only one that will work is if they're across from each other. So this is C5H12. So we have 1, 2, 3, 4, 5 carbons. Make sure I'm on the page, and 12. I've been doing a lot of these for other classes, and I'm getting very good at not writing below the line of sight. But if I do, and I keep talking, if I completely forget, I just redo the video. So know that eventually I will move it up, and usually with an apology. Okay, so you should be able to find the isomers of several different, any formula that I give you, you should be able to come up with a different bonding scheme. And you just have to keep in mind, what are you doing? You're breaking, if you have to break bonds to create the molecule, then it's a new one. If there's no molecule that you've drawn that can be bent into that shape, you have to break bonds, and it's a new one. Okay, draw 8 different conformations for octane using skeletal structural formulas. Now this is different than isomers. We're not going to break any bonds. We just know that the bonds are flexible. So we're going to show 8 different conformations. There are an infinite number. Every time the carbon moves by a fraction of a degree, it bends in any way, that's a new conformer or a conformation. So we just start out, we can just do this. And I said I wanted you to use skeletal because imagine even condensed forms for octane would be a kind of a monster. And I wanted you to use the skeletal structures just so you can see that you can, how they're used, and also save us some time. And then it's just a matter of bend them any way you want here, as long as they're different than the ones that came before. So this is pretty easy, as long as I mean this one would be considered different. You don't normally, a lot of times with the skeleton structures, they want you to stay in 90 degrees, but there's no reason that you have to. You can certainly make any kind of goofy one that you want. You don't have to stick with anything in particular. These molecules are very flexible, so when they're floating around in solvent or in the air, if they're gas, they're free to, or vapor, they're free to rotate in any way that their bonds will allow them to do that. Don't change the bonding scheme. It's a chain, so it's 1, 2, 3, 4, 5, 6, 7, 8. A lot of times when I give the students this flexibility, then they do something like this. I guess they get a little too freewheeling. So 1, 2, 3, 4, 5, 6, 7, 8. And they do that. That's wrong. By changing it into a ring or by branching it out, you've changed the structure. Conformation is just the same molecule, and it's just rotating. The atoms are rotating around the bonds, and these big molecules, these long molecules, are very floppy and can achieve all kinds of different conformations. So we have 1, 2, 3, 4, 5. Now I'm just getting kind of bored with, why did I say 8? But I guess oh, let's do like a staircase one. 1, 2, 3, 4, 5, 6, 7, 8. I can try to draw the first letter of my name. But just to show you that 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7. One more to do. Just do something like this. Don't think I've drawn quite this one before. Yeah, it looks a little different. So where you have an infinite number of them, just make them as different from each other as you can. You know, if you have a sense of whimsy, do whatever you want to do here, but you can't break any bonds, and you can't form them into rings. You can't branch them out. Whatever I give you, and also if I ask you to use skeletal structural formulas, that's what I want you to use. If I say you can't use them, you can't use them. So make sure you know how to work with all of these different types of structural formulas.